Directional derivatives. First one is for the scalar point function. Let phi p be any scalar point function. I have taken a point A, any given point, and there is another point P on this line L, right? Then if I take the limit P tending to A, phi P minus phi A, their difference, upon this distance AP. If this limit exists, then this limit is scalar and is called the directional derivative of the scalar function at A along the direction of the line L. And length AP is regarded to be as a positive length. So this AP is positive. This distance AP is greater than 0. Alright. Similarly, for the vector point function, it is denoted as vector fp. Instead of phi, I denote this as vector fp. So here also the limit p tending to a, vector fp minus vector fa over this distance ap. If this limit exists, then this will be a vector and is called the directional derivative of the vector function at A along the direction of the line L. Fine. So we get 2 points here. The directional derivative of a scalar point function at a point along any direction is scalar, and the directional derivative of a vector point function at a point along any direction is a vector, right? Then is the Cartesian representation of point functions and their directional derivatives. Suppose I introduce a system of 3 Cartesians, that is orthogonal Cartesians, OX, OY, OZ, and I have taken a point P with the coordinates x, y, z. Now let x, y, z be a coordinates of the point P. Then what is phi p? It is phi x, y, z. So scalar point function appears as a scalar function of the scalar variables x, y, z. Similarly, we have for a vector point function, we have a vector function of 3 scalar variables x, y, z. Phi is scalar and vector f is a vector. After introducing this, we have directional derivatives of scalar point function along coordinate axis. Now along the coordinate axis, suppose again this is your orthogonal Cartesians OX, OY, OZ. I have taken a point A and let its coordinates be x, y, z, and another point P, and the distance between them is delta x, the change in x. So what are the coordinates for the point P? This will be, yes, x plus delta x, and y and z remains the same. So we take point P on a line through this A drawn. Now this line is parallel to this positive direction of x-axis, right? Then this distance AP is your delta x. We have limit P tending to A, phi p minus phi a over AP. Let's see what is going to be the result. Now the limit P tending to A means, P tending to A means this distance delta x is tending to 0. So this is a limit. Again, you have to say about here that this distance should be regarded as positive. So here delta x is positive. So limit delta x is now tending to 0. Phi of p, that is x plus delta x, y, z minus phi x, y, z. over delta x. So this is nothing but your del phi over del x, right? Which is equal to, it is denoted as phi x. So denote this as phi x. So phi x is your directional derivative at any point A along the positive direction of x-axis, right? So the directional derivative at any point A along the positive direction of x-axis is phi x. Similarly, directional derivative at any point A along positive direction of y-axis and z-axis is phi y and phi z. So this is about along the coordinate axis. Now the directional derivative along any line. So for a line we need the direction cosines as L, M, N, right? Now for that, let phi be a scalar point function but having two qualities. It is continuous and differentiable. So we have taken phi to be a continuous and differentiable scalar point function. Then phi possesses continuous first order partial derivatives. So now you consider any semi-line through this A with direction cosines L, M, N, and A is having the coordinates x, y, z, and the distance of AP is R. Alright, then just remember this. Directional derivatives at A along a line with the direction cosines L, M, N is L phi x plus M phi y plus N phi z. So you have to remember this, right? Now the remark, if L, M, N are the direction cosines of the semiline AP, then if I take another point Q, a very opposite to that of P, and also equal at an equal distance, then what are the direction cosines for the line AQ? So here the direction cosines are minus L, minus M, minus N. So let's read the remark. If LMN are the direction cosines of the semiline AP, then minus L, minus M, minus N are those of the semiline AQ. Hence, directional derivative along AP is L phi x plus M phi y and plus N phi z. The directional derivatives along AQ will be minus L phi x minus M phi y minus N phi z, which are negative of each other. Just keep this in mind. Second is directional derivative along negative direction of the coordinate axis. Now along the positive direction of coordinate axis are, yes, what are the directional derivatives along positive direction of the coordinate axis? Just we have defined, that is phi x, phi y and phi z. Now for the negative direction, these will be minus phi x, minus phi y, minus phi z. Directional derivative of vector point function f vector. Now similarly for the f vector, at any point x, y, z along the positive direction of the coordinate axis. If we talk about the coordinate axis, then we must have the directional derivatives as, now for the vector point function, it is vector fx, vector fy, vector fz. But if we talk about its directional derivative along any line, then it will be a sum with the direction cosines. So this will be Lfx vector plus m vector fy plus n vector fz. Clear? Now the new term, that is a gradient of a scalar point function. Let's find out the gradient first. Let phi be any continuously differentiable scalar point function. we have the directional derivative as L del phi by del x plus M del phi by del y plus N del phi by del z. This is a direction derivative along a line, right? With direction cosines L, M, N. Can I write this as a dot product of these two, which is L, I plus M, J plus N, K dot product with I del phi by del x plus J del phi by del y plus K del phi by del z. Can I write like this? If you solve this dot product, you will get back this L del phi by del x plus M del phi by del y plus N del phi by del z. We know that dot product of, okay, you know this? Dot product of the same I, this will be 1. Dot product of j dot j is also 1. Dot product of k dot k is also 1. But dot product of I and j is 0. Dot product of j and k is 0. And dot product of k and I is 0. So by knowing this, if you solve this, you will get back this your left hand side. So this directional derivative along any line can be written like the dot product of these two, right? Dot product or a scalar product of these two vectors, where the former is your unit vector, which is dot product with this vector, the second one. Now this second one, this will be your gradient. Alright, this new vector is termed to be as your gradient. So it follows that directional derivative along any line can be obtained on multiplying the vector I del phi by del x plus j del phi by del y plus k del phi by del z scalarly. Scalarly means dot product with the unit vector along the direction. This is your unit vector. Okay, so we have to multiply this new vector with this unit vector to get the directional derivative along any line. Now I am going to define this new vector gradient. So for gradient, let phi be a continuously differentiable scalar point function. Then the vector function I del phi by del x plus j del phi by del y plus k del phi by del z is called the gradient of a scalar point function, and it is written as grad phi. So grad phi is equal to I del phi by del x plus j del phi by del y plus k, del phi by del z. This can also be summed up as summation I del phi by del x. Fine? So there is a note. A vector dot grad phi. This is the directional derivative of the scalar point function phi along the direction of the unit vector A. So A, this denotes your unit vector, right? And grad phi is summation I del phi by del x. These are your two notes. Now last one is the gradient of a constant. Now if phi is a constant scalar point function, then what is del phi by del x? Your phi is constant. So obviously del phi by del x is 0. Del phi by del phi is also 0. Del phi by del z is also 0. So from here, what is the value for the grad phi? Grad phi is what? I del phi by del x plus j del phi by del y plus k del phi by del z. Now each of these are 0. So this will be 0. So grad phi will be 0. Now the converse part. Suppose gradient of phi is 0, which means then del phi by del x plus j, I'm very sorry, del phi by del y plus k del phi by del z. This is equal to 0, which means when this can be 0, if each of these is equal to 0, each of the term, that is del phi by del x is equal to del phi by del y is equal to del phi by del z, each of this is 0, which implies phi is constant. So this is your if and only if condition. If and only if means this way is also true and other way is also true. So thus grad phi is equal to 0 if and only if the function phi is constant, means both the way the result is true. IFF means if and only if. So there is a result. The gradient of a scalar point function is 0 if and only if the scalar point function, that is your phi, is constant. Right? At the very last, the differential d phi. We have d phi to be equal to del phi by del x dx, del phi by del y dy, del phi by del z dz. We write d phi as this. Now again, can you write this as the dot product of these two? Yes. I'm writing I dx plus j dy plus k dz dot product with del phi by del x. Yes, what is this? This is your, very good, this is your grad phi. Del phi by del y plus k del phi by del z. So this is your dr, where r is xi plus yj plus zk. So can I write this as dr? Yes. This is your very well known now grad phi. Right? So the differential d phi is equal to dr vector dot grad phi. It is a dot product of dr vector and gradient phi, where r vector is xi plus yj plus zk. That's it. So next time we will going to introduce del operator and also some of the theorems we are going to do. Thank you for watching this video. Have a good and nice day. God bless you. Goodbye.